Okay, so I'm going to talk about a couple of laws of matter and Dalton's atomic theory. Now, the first law of matter that I'm going to talk about is the law of conservation of mass, which was discovered by Lavoisier. So the law of conservation of mass tells us that matter is neither created nor destroyed, or you could also say that matter is conserved. So the way that this was determined was by measuring masses of samples and tracking what happens to the mass when these samples underwent changes. Okay, so they would perform chemical reactions basically, and so they would measure how much stuff they have at the start and how much stuff they have at the end, and what they seen was they had the same amount at the start and end. Okay, and the amount I'm talking about is the mass. Okay, because remember, mass quantifies how much matter there is. And so what they seen was it didn't matter which reaction they were doing, the mass remained constant for all of them. And so the starting materials had a certain mass and the total ending materials had that same mass. Okay, and so we can confirm that with any reaction. And sometimes that comes in pretty handy when you don't know certain pieces of information about a reaction. You can narrow it down because you know the mass has to be conserved. Whereas, we'll look at how that gets more difficult later. But right now, let's just talk about that, how that applies to a chemical reaction. So a chemical change. So if we had the chemical reaction of methane or CH4 reacting with oxygen gas or O2, it would form CO2 and H2O. Okay, and in this reaction, what you have happening is bonds are breaking and bonds are forming. Okay, and so it might look like at first glance that you have some stuff to start with, and then that stuff is gone. Okay, and then you end up with some other stuff and it appeared. Okay, but it didn't really appear out of nowhere, and the stuff that you started with didn't disappear. Okay, and so you could actually break this down a little further. Instead of just looking at the picture or just looking at the regular chemical equation with the formulas, you can think about it as individual atoms. Okay. And so in this reaction, you have one carbon atom, 4 hydrogen atoms, and 4 oxygen atoms that you start with, and you end with those same atoms. The difference is that they're combined a little differently. They're bonded together differently, but they're all still there. Okay, so really, you're not creating or destroying anything. You're just rearranging it. Okay, now that's easy for us to understand looking at it now because we already understand matter is composed of atoms and molecules and so on. But remember, how this was determined was by tracking the masses. So we can go back and we can look at the masses of these things and confirm that, yes, the mass is conserved in this reaction and in any other reaction. So if you add up the masses of these things, what you would see is that a methane molecule or a CH4 molecule has a mass of 16.05 AMU. 2 oxygen molecules have a total mass of 64 AMU, and a CO2 molecule has a mass of 44.01 AMU, and 2 water molecules have a mass of 36.04 AMU. And when you look at that initially, you might think, well, stuff is changing, so I didn't lose or gain matter. Well, if you look a little closer, you'll see that you didn't. What you have to do is think about the total starting matter and the total ending matter. Okay, so you can sum all of that together, and really your total mass of reactants or starting materials is 80.05 AMU, and the ending mass is that same 80.05 AMU. Okay, so it is true, in fact, that the matter is conserved. It's all still there. It's just been rearranged. Now that unit AMU, in case you have not seen that before, that is atomic mass units. That's just a mass unit on a very small scale. Okay, that's typically only used when you are working on the atomic scale, which most of the time in introductory and general chemistry, you're not working on the atomic scale other than when atoms are being introduced. But if you were to do, say, nuclear chemistry, then it might be very common to use the unit AMU. So you see it occasionally in kind of intro and general chemistry. But most of the time we would use larger mass units on the scale of like grams. So that's the law of conservation of mass. Now that's one really important law that built the foundation for our further understanding of matter. Okay, so that's one of them, but I want to talk about one more that was really important in building that foundation. Okay, and the second one I want to talk about is the law of definite proportions. And this is one that was discovered by Proust. And so what this law tells us is that all samples of the same compound always contain the same proportions by mass of the component elements. Okay. Now realize that this is put in terms of mass because, again, at this point when this was developed, that's how they knew how to quantify matter, was by mass. Okay, so it's not stated in terms of atoms in something because atoms weren't, or that term wasn't developed at that point. But if we look at some examples, hopefully it makes it a little clearer what this is trying to tell you. So if we look at some examples, carbon dioxide, for instance, if you were to take different samples of carbon dioxide, and those samples can be any mass, and so I've got 3 different ones here in this example, and they're all different starting masses of carbon dioxide. But when those samples get broken down, okay, so if you split it all up into individual carbon atoms and individual oxygen atoms, and you actually measure the mass of those 2 pieces, then you could take the ratio of those masses, and no matter what starting amount you started with, the ratio of the pieces will always come out the same. So as you can see here from this data, the ratio for carbon dioxide always comes out to 2.66 grams of oxygen per 1 gram of carbon. Okay, so it's always a 2.66 to 1 mass ratio of oxygen to carbon for any sample of carbon dioxide. And then if we look at another one, look at another carbon and oxygen compound, because some elements can combine in different ratios. And in this case, it would combine in a 1-to-1 ratio of carbon to oxygen in terms of atoms. But again, remember, atoms weren't developed at this point. So if you were to look at just carbon monoxide samples of different mass and split it up into the carbon and oxygen, what you would get is, of course, different masses of carbon and oxygen because you started with different total samples. But if you take the ratio of those resulting masses, you would get the same ratio for every one. And specifically, you would get 1.33 grams of oxygen for every 1 gram of carbon, no matter which carbon monoxide sample you were analyzing. And so that mass ratio stays constant, okay, for those different elements. So those 2 laws, the law of conservation of mass and the law of definite proportions, those help to kind of lead the way to understanding a little bit better what makes up these elements. Okay, and so there was another scientist, Dalton, who took that stuff and put it together and tried to explain what that meant matter must be made up of. Okay, and so he developed the atomic theory. And in this atomic theory, he basically defined that there's a particle that makes up these things. And that particle he called an atom. Okay, and he said this is a very small thing. And so it's not something that we can visually see the individual pieces. Of course, you would have to have special instrumentation that they definitely didn't have back then. And so he basically said you have this very small particle, it's kind of your smallest unit of matter, okay? And he called those smallest units atoms. And then he also said that those smallest units, those atoms, are different for different elements, okay? But within an element, they're the same. So what he said is that atoms of a given element all have the same mass, they all have, the same chemical properties. Okay, so how they behave is the same if it's all the same element. Okay, whereas atoms of different elements are going to have different masses and different chemical properties. And then the third point of Dalton's atomic theory tells us that atoms are not created or destroyed in chemical reactions. And so that sounds a lot like the law of conservation of mass, right? And it basically is, but it's using the new terminology, okay? And so he's saying atoms are not created or destroyed, whereas the law of conservation of mass says that matter is not created or destroyed. And that should make sense if we accept that atoms make up matter, okay? So if matter has to be conserved and the building blocks of matter are atoms, then the atoms must be conserved. Okay, so that ties all together. And then there was a fourth point, and that last point was that atoms combine in simple fixed whole number ratios to form compounds. Okay, so basically he's saying that you have these smallest units, and that's what you have to work with. That's what you can combine together to form things. And so you can't take, half of an atom and combine it with a full different atom, okay? So at least you have to take these smallest units and combine with other things, okay? So even though in the law of definite proportions, we've seen that you have these fractional mass ratios, so 2.66 grams to 1 gram, or 1.33 grams to 1 gram. He was saying that you can't have fractional atoms combining. So those atoms are the smallest unit, okay? Whereas the mass could be fractional because you could have an atom that has a mass that's not a whole number, okay? And so that's basically, the foundation of what led to our understanding of what makes up matter, what makes up elements, okay? Now realize this is a theory. A theory, is kind of just a explanation based on what we know so far, based on everything that's been studied so far, trying to explain what is true or what is happening, okay? And so sometimes theories get proven wrong after more studies are done, or sometimes there's weaknesses in theories that then are proven wrong. Dalton's atomic theory isn't perfect. There are some pieces that aren't 100% true, which, as you learn more chemistry, you kind of figure those things out, or those will be pointed out. But this is a pretty good foundation, to understand, to help start to understand matter.